We're going to present the next series of talks, beginning with Dr. Hariharan Devarajan from Livermore National Lab, speaking about optimizing molecular dynamics with AI, like everything else today. Take it away.
Thanks, Quincy, for the introduction. This work has been done by a lot of people, which I'm going to go next. And the talk is a little bit different from all the talks that we have been having. This is kind of an experience of us as computer scientists working with molecular dynamics people's AI models and trying to explain to them why their IO is kind of messy and kind of what I went through, and talking about some of the performance characteristics of the applications that we potentially can use for our other users. This kind of analysis, I'm talking about a specific instance here that could be applied to a lot of AI models today. So hopefully it will be useful. As I said, this works involve a lot of people. This cannot be done alone, starting from the Flux team, part of which this project is, and then the MuMMI team, which is the molecular dynamics simulation team, who helped me run their models and test it and profile it and all those things. Of course, Jen is here from our group of storage team within Livermore, and Catherine, and then finally University of Tennessee. A lot of Dr. Toffer's students are working on this project in terms of understanding how could we optimize these kinds of workloads. So a little bit talking about the workload itself. So it's basically multi-scale modeling simulation for large molecular systems. It does a lot of, so I'm going to more go to talk about the systems aspect. So the systems aspect it basically does simulation, generates some training data, which is then trained offline with basically feedback mechanism, ideally part of a workflow. The whole thing typically starts disjoint, but then they combine everything together. And the idea of this model is to say that when we run simulations, we typically start with some set of initial conditions. Can we do that better in the workflow case during the instance? So that's why they're training this model essentially. A little bit about the data itself, because that's what we're here for. So it's a relatively small data set of 320 gigabytes in size total, spread across 600 files, 8,000 K samples, roughly about 16 kilobytes each arrays that we're working with, and unfortunately, data format is NumPy arrays, and I'll talk about why unfortunately in a minute. Then to do the training, they basically use PyTorch style data loader. Within PyTorch, you could write data in many ways, but they use the map style, which is basically saying, hey, give me this element, which for them, they do it with a batch size of 256, so they're getting 256 samples out of the 8,000 K samples within an HDF5. And then they have a raw computation step on the A100 GPUs, about 133 seconds. And for this test specifically, all the numbers I'm going to show, I ran this on Corona with 8 GPUs per node. And this node has 256 gigabytes of RAM and 3.2 terabytes of local SSD per node. Finally, the tools I'll be showing here is the data flow tracer, DF tracer, and I'm going to be showing some of the plots using DF analyzer and for better UI. So to look at the entire application as a timeline, so I just traced it with DF tracer and plotted it in Perfetto UI. This is the entire timeline of the application. If you see those, whatever that brownish color is or yellow color is, it's basically those parts are where the model is waiting for getting the sample. So you want to see less and less of that when you do training. The blue part is where you get the data and then you're doing computation on top of it. So within AI, a lot of stuff happened in parallel. For those who couldn't see my screen till now, I'm trying to show an application view of what happens within the training with NumPy arrays on this application. As I said, the blue bar is the computation. Within any AI application, essentially there are multiple steps of data loading. At the top level, you start with the definition of the data loader, which is like a task graph. And then during the runtime, these are executed and captured by processes, and those are the NumPy reader calls. each of these blue bars you see here essentially are one reading of one batch of samples together. And as you see here, there are too many small calls, which was a little bit surprising to us at first because these should not be as many as shown. So just to go a little bit more deeper into this, essentially as shown here, you will see a lot of small read calls because of the way NumPy array does stuff. Here, the read calls are not only data calls, there are metadata calls. Actually, the bulk of the reading time is for the NumPy arrays is spent on LSTAT to figure out what is there within the file, which is loads of IO calls there just to figure out things along the way, and they do a lot of things here. So just as a summarization, again, this is a view from the DF analyzer. You can see how many nodes it was run with and computation. Typically, as I said, this is 32 node run, 8 GPUs. So you have some number of GPUs used, and then you do, by the way, this is not a 32 node run. Maybe, anyways, it's not important. And then the I/O part here, which is the more important part, is that on the 32 nodes, the I/O runs on CPUs using Spawn within PyTorch. So you have a lot of processes doing I/O. It creates about 18 million events for this workload. 604 files are accessed, including some application level files. Finally, in terms of I/O time, you can see basically that the computation is a very small portion of the entire timeline, which about less than 10%. And the rest of it is actually I/O time. So that was one of the reasons we were approached when trying to look at this problem. And one of the main things here is that they were doing too many operations for the number of samples they were accessing, and so that's what we wanted to do. So from this, we looked at the bandwidth. It had spikes basically along the way because there were a lot of metadata calls happening and then a lot of data calls happening. So that's kind of the idea. But if you just look at data calls, they were not badly sized. So there is a lot of unexpected behavior coming from NumPy array, and that's why we kind of moved to trying to look for how could we do this with HDF5, but going a little bit more deeper into this figure, because you'll see some of the figures later on, is the blue line here shows the POSIX of the time. The POSIX, the dotted line is the bandwidth, which is the y-axis, and the y2 axis, respectively. And then we are also plotting the transfer size. And the whole thing is plotted on a timeline. So basically, we take every 1 second or 10 seconds, whatever it is, and aggregate this data and calculate bandwidth across all these processes correctly. So as I said, the first thing I noticed was there was a lot of small I/O happening and a lot of metadata calls happening, which was not expected. And from kind of an HDF5 person using this, I thought that would be a great use case for that. So the first thing we did as soon as we ran this, we had faster execution time because it stopped doing a lot of I/O calls to the file system. So straight out of the bat, that helped in terms of performance. Essentially, if you see each getting of samples itself becomes shorter. If you kind of zoom in, this is exactly how I would expect I/O to happen for these kinds of workloads. You have one metadata call at the start and then large PDs essentially happening throughout the timeline. And that kind of overall gives you much better performance on your file system. So that's basically what I mentioned. And out of all this, so out of all this, as I said, now you certainly see larger reads happening in bulk, and then that reduces the I/O time you would see on top to significant. It was 2700 before. It has become almost 30 seconds now of I/O time, and so most of the I/O you see now is very well overlapped with compute itself. So, and there is some prefetching which happens because of it. Some of it is not overlapped. So in the timeline of these things, if you look at the y2 axis from the previous figures, it looks similar, but overall average bandwidth within the application was much higher, so actually much faster. It was almost 30x faster in terms of I/O. And overall, if you just look at the workloads runtime, it was almost 13.4x faster. In terms of, so once we did this, as I mentioned, there are node local storage within these nodes, and that was our next step to take this HDF5 optimized application and further enhance it with node local storage. That's where the DYAD project comes in. So basically, DYAD is originally built for consumer producer workflows where you have a producer trying to produce data and some other consumer trying to retrieve that data. Typically, within a lot of workflows, what would end up happening is you would use some form of shared storage because the workflow would be deployed on large number of nodes, and so you can't really you will have to either manually use wherever possible node local storage or else just default to shared, which is what most workflows do. So the goal of this project originally is to help building these kinds of things. It's more of a portability layer where users don't have to think about node local storage or shared storage. DYAD manages node local storage with the same semantics as a shared storage, so it has its own synchronization mechanism to wait for the data to be there. So you can essentially share data between producer and consumer efficiently. In the context of AI, you can kind of think about this as a caching layer in the sense when the first read and the first epoch happens, you could cache that data on the node local storage. You can think of it as a producer, and then other processes on the same node or different nodes could read from this cache efficiently. So that's kind of the context of how we use it, because this is more built originally for kind of write once, read many, which is more popular within workflows. So it could be nicely tailored to AI workloads here. So essentially, producer here, as I said, is the first AI worker who read the sample and puts it into the notebook cache. Originally, you would do this with shared storage, and so that's where DYAD comes in, and the consumer is some other process on different node or same node trying to access the cache. So essentially, what happens with DYAD is that you use node local storage to produce the data, put it locally, and then use automatic synchronizations using Flux's hierarchical key value store to understand if the data has been produced. The consumers will implicitly wait for that, so there is no explicit need of communication here. And then once the data is available, the data is transferred using a pull mechanism from that node into the client who wants to consume the data. And then there is the data is stored on the local file system there, and it gets consumed. So here the granularity is per file. So in the context of the AI workload, basically the whole file is moved from the producer to consumer, and then samples would be read the same way as if it was present locally by the consumer. So doing this optimization essentially it keeps the same kind of IO behavior because, as I said, you just move the whole file there. But it significantly improves the IO time because now you are suddenly, after the first epoch, you will start seeing a lot of cache hits on the system through DYAD on node local storage, which will significantly improve your performance of IO. And that's what is shown here, that so the bandwidth here from kind of 10 gigabytes have now gone to 100 gigabytes. That's purely because, and if you see initially the bandwidths are lower, and then it starts going up essentially. So that's kind of the idea here is during the first few epochs, it will cache more and more data depending upon the scale because this is data parallel training. So it has to map all the data. Overall, if you just look at IO time, there was a 7.5x speedup. And overall timeline was reduced by almost 1.9x. Some interesting key learnings that I want to take away from this is a lot of AI applications use very different formats than what we expect, and so that creates the majority of IO performance bottlenecks. So another interesting aspect that I found here was because once I used HDF5, one of the other things I was thinking was, can I force HDF5 not do too many small metadata accesses to understand the data? So I was doing chunking, but that did not help because the sizes of the request itself was very big, so it didn't help on the file system I was running in. Rather, it hurt the performance. So this was one of the nice cases where chunking actually screwed up the performance. So that was an interesting finding. Typically, I use chunking as my basic mechanism to help do better IO, but this was not the case here. Prefetching policy of PyTorch itself is not very aggressive. There is a lot of recent work going on to kind of try to make it more tightly prefetching. Typical mechanisms use write your data loader smartly, which most users don't. That's really bad. And finally, using node local storage with RDMA really helps to share data for AI workloads because it's typically read-only and there is no updates happening. And of course, interacting with domain scientists is fun because you have to explain to them why the data format is bad, because they actually changed from HDF5 simulation data to NumPy's array to do this training, which was a fun thing for me. So I just told them not to do that. So that was a very fun experience. So just to conclude this, NumPy arrays typically do a lot of small accesses and do a lot of computations, which could significantly slow down training. HDF5 format, of course, helps, and especially in cases where you do large IOs, this could be really beneficial, like in this case. Utilizing node local storage could help you further optimize your workloads to share data. All the codes in the analysis I showed are open source and are available in this link. And I again want to acknowledge all the work that all my collaborators did for making this work possible. Is that good on time? Yes, great. That's good.
Thanks, Hari. Any questions I want to ask Hari? I think a ton of work there.
Did either the NumPy arrays or HDF make use of compression?
No, because they don't by default use it.
Would you do things if they did? Did it help?
It's a difficult trade-off because the distribution of their molecular dynamic samples are not very compression friendly. Let me put it this way. So they are very uniform sometimes, and so they don't end up compressing well in terms of values. So they don't have hotspots of certain values being more than the others.
Right.
So yeah, so that's why they ended up not compressing the data. Also, we'll have to see how does that change in terms of the trade-off of reading it and decompressing it versus just reading it out. There is a lot of caching effects happening, so I'm not sure how that will directly impact, even if we did so.
Any other questions? Okay, let's bring the next speaker.
Thank you.